Motion problems and quadratic equations. We've actually seen motion problems back when we were working on rational equations. This time it's going to be a little bit different. We're going to have to set up our equations in a similar way using some rational equations, only we're also going to need to use our quadratic problem solving skills to solve the equation. So in this question, an airplane completes a round-trip journey of 2,000 miles each way in 9 hours. And we're told that the plane flies at a rate of 450 miles per hour. We want to know, what was the wind speed? So before we jump into the math of solving this problem, what we're going to do is draw a picture and then discuss the assumptions we're making just by setting up the problem the way we do. So I'm going to start here drawing a dot where the plane is beginning, and I'll draw a quick little picture of a plane. I'm never much of an artist, but let's see what I can do. There's my airplane. Not too bad there. There we go. There's my airplane. And the plane's going to fly. We're told it completes a round trip, so it's going to fly one direction, land at its destination, and then return. So flies one direction, lands at its destination, and then returns. And we're told that it's flying in wind, and we have to get that. We have to understand that from this last part that asks, what's the wind speed? And understanding that this is what we're being asked for in the problem, I'm going to call it the variable W. And let's draw it into the problem. So when the plane is flying to its destination, I'm going to say it's flying into the wind. And when it's flying back to its starting point, we'll say it was flying with the wind, or with a tailwind that pushes it back. And just by writing or drawing arrows to show the wind speed, I'm making a couple of assumptions. So the first assumption that I'm making is that the wind speed is consistent in direction and speed. So that means that the wind isn't speeding up and slowing down, so maybe it's blowing 90 kilometers an hour on the way there and only 40 kilometers an hour on the way back. No, we're going to assume that it's constant over that whole 9-hour stretch. And we're also going to assume that it doesn't shift direction, so going from the right to the left at the beginning and then going from the left to the right later. And we're also assuming that the wind blows directly into or from behind the plane. Because we have to make that assumption to be able to solve this problem with our skills that we've learned in this course. If we drew the wind as blowing from the south to the north, for example, and it wasn't blowing in the direction that the plane was flying, or exactly against the direction that the plane was flying, then this problem would all of a sudden become a physics 12 problem. So we're not going to do that. We're just going to assume that it's blowing directly in line with the plane. And finally, the last assumption that we're making is that we are ignoring takeoff and landing. And this is important because the plane is very likely speeding up as it takes off and then getting to its highest velocity. And then as it comes into the landing strip where it's landing, it's going to slow down, come to a complete stop, let off passengers, take new passengers off, and then start up again. And we're ignoring that the time that it's on the tarmac and the amount it has to speed up and slow down at these different times, and we're just assuming that it's going at a constant speed the whole time. And now that we are through on those assumptions, we're ready to get to the problem solving. So I'm just going to draw a little sketch of what this trip looks like. So the plane flies there and then returns. And we know that this distance is 2,000 miles. From just one way is 2,000 miles, so it's going to be 4,000 miles in total. And now we've got a little picture. We know that there's a wind speed as well. I'm going to draw it right in the middle. We're just going to say it's blowing to the left. It actually doesn't matter. This problem is symmetric. Whether the wind is blowing against it at the beginning or with it at the beginning, it's going to be doing the opposite on the return journey. So it doesn't really matter which direction we draw the wind speed, but we're just going to pick a direction and be consistent with it. That's the key. And now we're going to get into our motion formula. So we know that this is a motion problem, and we're going to have to use our knowledge of speed, distance, and time. So you'll recall that the speed is equal to the distance divided by the time. Distance something travels divided by the time it travels for. And because this is a problem that's linking the two halves of the journey with time, we're told that the total time it's going to take to complete is 9 hours, then we're going to rearrange this formula so that time is equal to distance over speed. Because really what we're going to have to do to set up an equation is relate these journeys to the time it takes. So I'm going to call that the time it takes to go on the first part of the journey, time 1. So I'll say time 1 plus time 2 is equal to 9 hours. And we don't know what time 1 and time 2 are. Sorry, I'm just going to rewrite this over here. Time 1 plus time 2 equals 9 hours. And we don't know what time 1 and time 2 are. So what we're going to do is we're going to replace them, because we don't know anything about the amount of time it takes for the individual trips there and then back. We're going to write them using our as distance over speed. So time 1 is the distance that the plane goes at the first speed, and time 2 is the distance that the plane goes at the second speed, and combined those are 9 hours. And we know that the distance is 2,000 miles each direction, but what about the speed that the plane goes? Well, so that we know that the speed on the trip there is going to be equal to, so this is going to the right, this beginning speed here. We know that the speed's going to be 450 miles per hour minus the wind speed as it blows back against the plane. And then that second speed, the speed on the way back the other direction, is going to be 450, plus it's going to get a bonus speed from the wind. It's going to get pushed as it flies in the direction of the wind. So I can replace now these variables in this equation. So the distance is 2,000 miles, and the speed on the way there is 450 minus the wind speed. And I'm going to add 2,000 miles divided by 450 plus the wind speed is equal to 9 hours. So now I've set up a rational equation, and I just have to take the time to solve my rational equation. And to do that, I'm going to multiply everything by 450 minus W, 450 plus W, to eliminate those denominators. And now I'll go ahead and do that. So 2,000, and then the 450 minuses will cancel, so I'll get 450 plus W, plus 2,000 times 450 minus W. And then when I multiply these two things by 9, I'm just going to do 9 times 450 minus W times 450 plus W, because there's no cancellation there. And now I just want to expand everything out so I can start grouping together my terms. Whoops, I got to make sure that's a plus there in my last bracket too. So now I'm going to expand out. So just using my calculator, 2,000 times 450 is 900,000. Be careful with your zeros. Plus 2,000 W, plus another 900,000, minus 2,000 W. And on the right-hand side, I'm going to start just by foiling these brackets. And so when I do that, I'm going to get 202,500 plus 450W minus 450W minus W squared. And we're seeing a lot of cancellation, which is really nice. And then I'm going to multiply that 9 into the brackets on the right-hand side. So 900,000 plus 900,000 is going to be 1,800,000. And then on the right-hand side, I have 1,800,222. I'm messing my big numbers up. 1,822,500 minus 9W squared. Okay, this is looking good. And now I'm just solving this quadratic equation, which is actually going to be really nice because I can solve it with the square root principle. So I'm going to subtract this constant over to the left-hand side. So subtract 1,822,500 from each side. So that's negative 22,500 equals negative 9W squared. Divide by negative 9, divide by negative 9. I'm going to give myself a little bit more room to work up here. So now I have, divided by negative 9, 2,500 equals W squared. And now I can apply that square root principle to say that W is plus or minus the square root of 2,500. So taking the square root of that in my calculator, I get plus or minus 50. And I'm going to reject the negative solution because the wind speed can't be negative. I'll say wind speed must be positive. So there we go. I've solved my problem. The last thing to do is write as a sentence. So the wind speed is 50, and I need units for it. Because everything is in miles per hour, miles is my distance, hours is my time, the other speed was in miles per hour. This is 50 miles per hour. And there's my answer. Now, does that seem reasonable? I mean, honestly, it's a very fast, heavy wind speed. In kilometers per hour, that would be something like 80, 90 kilometers an hour, I think. So it's pretty heavy wind over 9 hours, but it's still a reasonable speed for wind. It's heavy wind, but it's a reasonable speed. And so I'm happy with our solution. And that's the sort of method you're going to have to follow to solve these motion problems. Some equations will be solvable with the square root principle. Some you might need to factor, and potentially you could also have to use the quadratic formula to solve whatever quadratic equation you're left with.